Today we will be discussing very introductory understanding about stability augmentation system, and the basis is you understand that when we took the determinant of this matrix, which was stability matrix, and the exact solution as the equation of this form H4 plus Bs cube plus Cs square plus Ds plus E equal to 0, determinant of this matrix. And also we realize the roots lambda 1, lambda 2, lambda 3, lambda 4 for longitudinal case, for lateral directional case, they depend on the value of A, B, C, D, E, their magnitude and their sign, and in turn it depends upon the dimensional derivatives, and dimensional derivatives in turn depends upon the non-dimensional derivatives and of course inertia properties. And we also realize that if we plot imaginary and real part of the root, we wanted them either this way or maybe on the real negative side. What was important that root should lie on the left half plane to ensure that there is a convergence. But the question comes, how far from the real and what is the magnitude of this if it is a complex conjugate? That depends upon what? Whenever we think of complex conjugate, we know there is a natural frequency and then there is a damping ratio. And we need to change omega n and zeta depending upon our requirement, which is decided by the handling qualities of an airplane. Today we will be discussing about how do I change this omega n and zeta to satisfy the handling qualities of an airplane. These handling qualities we will be talking about, but to begin with, you understand that they are primarily characterized or benchmarked through the values of omega n, zeta or their product for different modes, for longitudinal short period, for phugoid, for lateral directional, roll mode, then for Dutch roll frequencies, but all are focused towards omega n and zeta, or sometime time to half amplitude, T half. These are all the concepts which are there in when you analyze the second order system. Okay, so we will take first, suppose we are dealing with longitudinal case. I will give one example, let us say for short period case, short period mode. And what we are discussing now? We are trying to see how stability can be augmented during flight. Okay? So, we say SAS, stability augmentation system, or in short we say SAS. How do I approach? I said our target is handling omega n and zeta. Let us say if it is omega n, and if it is a short period, by now we know we have analyzed pure pitch, we have analyzed an approximate short period mode by simplifying the exact equation. Also we know the exact solution as well. But for a designer, he will always try to start with a simpler thing. So, omega n, if you see for a pure pitch, will be root minus m alpha, and this you know is equal to minus half rho v square S C bar Cm alpha by I y y whole under root. You could see that this omega n will go on changing with rho. It will change with v or v square, or rho I can write because in the root rho to the power half and v. The point is, as going higher and higher, natural frequency short period mode will go on reducing. As I increase v, short period natural frequency will go on increasing, or in totality if I say omega n increases with dynamic pressure, that is half rho v square, or under root, this is under root of q. So either I can realize with altitude, as it goes higher and higher, omega n reduces. With increase in speed, omega n increases. With higher altitude, omega n decreases, because with higher altitude density goes down, and with increase in speed, omega n goes on increasing. Or also in totality I can say omega n changes with dynamic pressure the airplane is experiencing. That is primarily the environmental condition, right? However, from aerodynamically, you could see that omega n changes with Cm alpha. And what is Cm alpha? Cm alpha, if you recall, it is a measure of static stability. Or in turn, it is a measure of stability margin. Let us say if there is a requirement that omega n be increased at some point in the flight. What is the way to do it? Omega n to be increased, that means I need to increase Cm alpha in flight. Keeping rho v constant. That is, at a given altitude, at a given speed, I want Cm alpha to be increased so that omega n is increased. How do I do? In flight. So let us say the approach is simple. This is basic understanding should be clear. This is the aircraft model, and here there is a elevator input going here, and here I am output I am getting as alpha, angle of attack. What I do, I tap this alpha and multiply with a gain k, and then feed such a way that delta E is k alpha. So this is the delta E, which is proportional to k alpha. Somebody may ask, how do I measure alpha? Alpha can be measured by using angle of attack vane. It could be measured by pressure probe. All these things we have discussed in the last course. How Cm alpha is changing, let us see. Because of this delta E, which is given as k alpha, what is the delta Cm we are introducing in the airplane? That you know, Cm delta E into delta E, which will be equal to Cm delta E into k alpha. So this is delta Cm introduced by giving delta equal to k alpha, and then from here delta Cm by alpha, which is delta Cm alpha, which is nothing but Cm delta E into k. So this understanding is there. if I want to introduce additional delta Cm alpha, or artificially I am changing the stability matrix for that time, I can easily do it by feeding alpha and deflecting elevator for that time proportional to k alpha. Okay. How much k? Let us say we have Cm alpha basic, that is, which has been designed from the beginning depending upon wing location, tail location, CG, etc., etc. This is available for the airplane. Now, we want Cm alpha SAS, some value which I am targeting. And how do I get that value? I get that value because this corresponds to some omega n basic, which is nothing but minus m alpha basic. Now, I want omega n SAS, that will be under root minus m alpha SAS, right? And this is, I know, equal to under root half minus half rho v square s c Cm alpha by Iyy, and this is Cm alpha SAS. Okay. So, if I know this value, how much I need, this is known. And if I know at what altitude I am flying, I know SC, I know Iyy. So, from here, I can easily find out what is Cm alpha SAS required. You understand this? We know what is Cm alpha basic, that is omega, and from there I know what is omega n basic, that is given by m alpha basic. And what is the Cm alpha required through SAS? Why do I require it? Because I want omega n nu. Correct? So, this Cm alpha will be nu, and from there I need to find out how much Cm alpha SAS is required. And what will be Cm alpha SAS? Cm alpha SAS required will be Cm alpha nu minus Cm alpha basic. Already Cm alpha basic is there, right? And that is what the role of the SAS, which I write as delta Cm alpha SAS. Clear? Should I repeat again? Cm alpha basic you know from the design, which is given by under root of m alpha basic. And if I further expand it, I find for omega nu for a given altitude and speed, what is the Cm alpha nu required? That means, next question is how much Cm alpha SAS required, so that delta Cm alpha SAS gives the additional delta Cm alpha, which is nothing but Cm alpha nu minus Cm alpha basic. Okay. And then you know this Cm alpha nu minus Cm alpha basic, which is delta Cm alpha, that is equal to Cm delta E into K, right? So, what is K? K becomes Cm alpha nu minus Cm alpha basic divided by K, divided by Cm delta E. And textbook you will find this is also written as Cm alpha required minus Cm alpha basic divided by Cm delta E. That gives the value of K. Okay. But there are restrictions on K, because do not forget, finally whatever Cm alpha nu you are getting, that has to again go back to this. has to be plugged in into that equation and see whether the roots are what you are looking for or not, right. So that restricts, you cannot take too high value of k, you cannot take too low value of k. So those are of engineering aspect, but fundamentally the approach is like this. This is one. Then you have to also see that by doing this, whether any other parameters are changing or not, especially aerodynamic parameters. Now you could see that CL, there will be change in CL also, because CL alpha is given by CL alpha into alpha, the additional CL. And if you see CL, delta CL, because of delta delta E, which I have given as delta equal to K alpha. So this will be CL delta E into K alpha. So delta CL by alpha, which is nothing but delta CL alpha, will be given as K into CL delta E. So by giving a SAS deflection through using delta equal to K alpha, it is fine. You have been able to change CM alpha basic to CM alpha nu or CM alpha required, so that omega n is what you look for. But do not forget, it is also changing the value of CL alpha. So that also input will go here, and you check whether still you are getting the roots on the left hand side and to the desired location, so that you have correct value of omega n. Okay, because this we have started using the very first approximation, we have taken pure pitch case, and that is the way to start, because otherwise it becomes very complicated. Okay, so this sort of a iteration goes on, right. Now if you want to look for how do I change damping ratio, let us also see. Once you have understood this, how to change damping ratio should also become very simple for you. Let us not forget, we are talking about longitudinal case. Let us say now we want to change zeta. Again, we will take help of pure pitch for longitudinal case to start, and you know 2 zeta omega n equal to minus mq, and zeta is proportional to mq, or zeta is proportional to cmq from the pure pitch equation. Now you see, let me write pure pitch. We are talking about longitudinal, so starting with this. So suppose the airplane has zeta basic. Now you want to increase the zeta to zeta nu. That is the question. Because you are not happy, you find that as I am going higher and higher, the zeta is also reducing, because zeta, if you see here, from mq is nothing but half rho v square s c bar cmq by iy, and other terms are there. So you know that very clearly zeta will change with altitude as well as dynamic pressure. So you have a zeta basic, which you have designed the airplane for a given altitude, but you are now operating at different altitude, let us say. So now you want a zeta nu, so that your airplane has the right type of damping ratio as dictated by, let us say, handling qualities. So how do I approach? Again, the method is simple, understanding wise. If this is the airplane and this is the Q pitch rate, and this is what I do. Now I tap Q pitch rate using a gyro and feed delta delta E equal to K into Q. So proportional to Q, I feed elevator deflection. I mean, as long as Q is there, I require this. Okay, right. So now what will happen? If I do this, again, what is delta Cm? That will be Cm delta E into delta delta E. That is equal to Cm delta E into K Q, right? That is how I have deflected. And CMQ is defined as dCm by dQc by 2U1. So I divide both sides by QC by 2U1. So I get CMQ equal to, from here, equal to Cm delta E into KQ. I write it delta, or for your clarity, let me write delta Cm divided by Q C by 2U1 to get CMQ by definition. So I divide it by Q C by 2U1, and that gives me QQ gets cancelled. This gives me 2U1 Cm delta E K Cm delta E 2U1 K 2 by C is here, right? Clear? I hope I have not done any mistake. Cm delta into KQ. So I am dividing Cm delta into KQ by QC by 2U1. 2U1 goes up, C is here, right? K and Cm delta E. Right? So this is delta CMQ, which I am generating by feeding Q, which is measured through a rate gyro, and deflecting the elevator proportionally with Q. Right. Now the question is, I know zeta basic, it has corresponding CMQ basic, and for zeta nu, I need CMQ nu. So how much additional CMQ I require will be CMQ nu, or whatever required, minus CMQ basic. That should be equal to delta CMQ, and that should be equal to 2U1 by C into Cm delta E into K, or I can write K equal to CMQ nu minus CMQ basic divided by 2U1 by C into Cm delta E. The CMQ nu, many textbook will tell CMQ required. Okay. So don't, I purposely put CMQ nu so that you know that. Suppose CMQ was, basic was minus 18 for zeta basic, but for CMQ is minus 25 for zeta nu, then this minus 25 minus 18 is delta CMQ. That comes here, and rest is here, right? Again, whatever value of K you get, you have to again feed it back to that AS4 plus BS cube plus CS square plus DS plus E equal to 0, and check whether the aircraft is still dynamically stable or not. That is also very, very important. And what sort of route or pair you want, what exactly you want those routes, so that you get the correct value of zeta and omega n all together, right? So you have to go collectively with everything together, you have to work. But at the same time, you must also understand that as I am giving a feedback on Q using a gyro, so you know that CL also has a component CL delta E into delta E, right? Like it has CL alpha into alpha, blah, blah. So delta CL, because of delta delta E equal to KQ, what will happen is, it will, here also has CLQ into QC by 2U1, like this all terms are there. So this will tell you CL delta E into KQ. So again, you find additional CLQ, delta CLQ be seen by the airplane, and that will be delta CL by QC by 2U1, that is equal to CL delta E into KQ by QC by 2U1. So this becomes 2U1 by C, CL delta E into K. So whatever K you have identified from here, make sure this CLQ, which was basic, that also gets altered by this delta CLQ, which you have to also correct once you are solving these exact equations, right? So this is, in a nutshell, I have given you the approach. We'll solve one or two examples on this so that you understand. And similarly, we'll build for directional case, lateral case. And if you understand this much, you yourself will be able to extend this understanding to lateral directional case. We'll do that in the next class. And I'm trying to talk about handling qualities soon. Okay? But I thought before I talk about handling qualities, you should demystify all these SAS and all. These are basically this is the concept. That's all, right? Okay. The rest is solving Sixth-law equation of motion or finding a transfer function, how to find their solution. The understanding is this. Okay. Thank you very much.